The future of propulsion is not in spinning faster, but in interacting smarter.
Oh, I like that.
Yeah, right. I'm looking at a schematic right now for a new kind of marine engine, and it is missing the one defining feature that boats have relied on for, well over a century.
Yeah, it's wild.
There is no propeller, no spinning blades. It's just this clean, direct mechanism that is basically designed to punch the water in a straight line.
It is a genuinely jarring visual when you first see it. I mean, especially if you spend any time around maritime engineering.
Right.
The device is called the N5 prop, and the graphic, it proudly emphasizes two core promises, which are no rotation and direct thrust.
Which brings us to our mission for you today. Welcome to the Deep Dive. We are exploring this fascinating engineering paper authored by Dr. Lev Nemotin from N5 Digital, Inc.
Yeah, it's a really dense but amazing paper.
It is. The paper explores this concept called phase-structured marine propulsion. So our goal today is to figure out how a linear electric engine, so an engine that pushes back and forth instead of spinning in a circle, might just completely rewrite how vessels move through the water, from small boats to massive cargo ships.
Yeah, and to really grasp why Dr. Nemotin's proposal is such a massive leap, we should, probably start by talking about the water itself.
Okay, let's do that.
Because why spinning a blade through water isn't actually as perfect a solution as we tend to assume.
Well, yeah, because if I think about a standard propeller, it seems incredibly efficient. I mean, you turn a screw, the boat goes forward. It is intuitive.
Right, it makes sense.
And it has worked for over 100 years. So what is actually wrong with it?
Well, it works, sure, but it wastes a shocking amount of energy doing things that do not push the hull forward.
Oh, really?
Yeah. Think about what a propeller blade is actually doing down there. Because of the angled pitch of the blades, it isn't just pushing water straight back.
Right, because they're tilted.
Exactly. It is violently throwing water sideways, radiating energy outward, and creating this massive swirling vortex in the wake of the boat.
Oh, wow.
So all that rotational energy churning the water sideways, that is battery power or, fuel you burned that contributed absolutely nothing to your forward momentum.
So you are basically spending a huge chunk of your energy just, like, stirring the ocean.
Precisely. You're just making a blender. And that is before we even talk about something called cavitation.
Cavitation, what's that?
So if you try to push a boat faster by spinning a propeller at extreme speeds, the pressure on the backside of the spinning blade drops so dramatically that the water actually boils for a split second.
Oh, really? Boiling water just from spinning a metal blade?
Yes, cold boiling due to sudden pressure drops. It creates these microscopic vapor bubbles.
That sounds intense.
It is. And when those tiny vapor bubbles collapse just a fraction of a second later, they create these intense micro shock waves, and they literally eat away and pit the solid metal of the propeller blade.
So the engine is basically destroying itself.
Yeah, with traditional propulsion, you have a hard physical speed limit. You can only spin so fast before you start destroying your own engine and wasting a majority of your power.
Okay, let's unpack this.
Yeah.
Because propellers waste energy sideways, they suffer from slip, and they literally eat themselves if they spin too fast.
Right.
That paints a really clear picture of why we need an alternative. Which brings us to Dr. Nemotin's solution, the N5 prop.
Exactly.
I want to make sure everyone listening can visualize this. If it's not a spinning screw, what does this linear stroke actually look like underwater? Like, are we talking about giant robotic flippers on the back of a boat?
Think less like a biological flipper and more like a high-tech oscillating plate. Or like a massive hydroacoustic driver.
Yeah.
Imagine a flat, heavily reinforced surface at the rear of the hull. This plate shoots straight backward, physically shoving a solid column of water directly aft, and then it rapidly retracts into the housing to strike again.
So it's like a boxer throwing rapid-fire punches at the water.
That is a very apt way to visualize it, yeah? But the true genius of Nemotin's paper isn't just the linear punching motion.
What is it then?
It's the timing, the speed, and the force of those punches. That is where the term phase-structured comes in.
Phase-structured.
Right. His core argument is that thrust shouldn't be treated as a single homogeneous event. The demands placed on a boat's engine change radically depending on the phase of movement it is currently in.
Wait, but water's just a fluid. I mean, if you punch it slowly, your hand just slips through it. If you punch it fast, it feels like hitting concrete. How does an engine account for that?
Well, that is the exact hydrodynamic wall Nemotin is trying to overcome. So let's look at the startup phase.
Okay.
Imagine a heavy cargo vessel at a dead stop in the water. To overcome the vessel's resting inertia, what the paper refers to as static hydrodynamic resistance. You cannot just use rapid, shallow vibrations.
This wouldn't go anywhere.
Exactly. You need a massive, slow, incredibly forceful push. You need that oscillating plate to grab a huge, heavy chunk of water and shove it backward with immense torque.
Oh, I can picture that. But once the boat is actually moving, that slow, heavy push isn't going to do anything, right? The water is already rushing past the hull way faster than your plate is pushing.
That's spot on, and that triggers the next phase. Once the vessel is cruising, the propulsion system has to fundamentally shift its behavior.
So it punches differently.
Yes. It needs to utilize much higher stroke frequencies. So incredibly fast back-and-forth movements, likely with a much shorter travel distance, to maintain an effective grip on that rapidly moving stream of water.
That makes total sense.
Right. The entire premise is that the physical stroke adapts dynamically to exactly what the fluid dynamics require at any given millisecond.
Okay, but I'm looking at the engineering schematics here for how we actually power this oscillating plate. And something feels incredibly counterintuitive.
What's that?
Well, we are talking about using modern electric motors to power these new marine engines, but electric motors are round. They spin.
They do.
If we want a straight back and forth punching motion, aren't we fighting the very nature of the electric motor itself?
You know, you have just stumbled onto what the paper highlights as a major historical reversal in mechanical engineering.
Historical reversal.
Yeah. To understand it, look back at the last century of the internal combustion engine. Inside a traditional gas or diesel engine, you have miniature explosions forcing pistons up and down.
Right.
That is linear reciprocating motion in its purest form.
Oh, I see where you're going. But we never used that up and down piston motion directly to push the boat or the car.
Nope.
We took that linear energy, attached it to a heavy, complex crankshaft, and converted it into a spinning motion to turn a wheel or a propeller.
Exactly. The entire mechanical architecture of modern global transportation was optimized to transform a straight line into a continuous circle.
Wow.
But now, as the maritime industry moves toward electric power, we are starting from the exact opposite position. As you pointed out, electric motors naturally produce beautiful, smooth, continuous rotational output. They want to spin.
So to achieve Neymoten's vision of a direct linear punching propulsor, we have to run the historical playbook in reverse.
Pretty much.
We have to take the perfect natural rotation of an electric motor and invent a way to convert it back into a straight line.
What's fascinating here is that this is the first major hurdle. I mean, generating massive amounts of electric power is a solved problem. We know how to do that.
Sure.
The true engineering challenge Neymoten outlines is what he calls adaptive motion control across changing regimes.
Okay, adaptive motion control. So basically, how do you take a continuously spinning electric motor and use it to throw a slow, heavy punch 1 minute and a rapid, shallow jab the next?
Exactly. And doing all that without completely destroying your own machinery.
Right, so let's look at the first way the paper tries to solve this. Neymoten explores two distinct engineering architectures to make this linear stroke a reality.
He does.
Architecture 1 is called the rotary conversion compromise. I assume this means we keep the spinning electric motor, but we jam a mechanical transmission in the middle to translate the movement.
Yeah, it is the most logical first step for an engineer to take. We have spent decades perfecting rotary electric motors.
Right.
They're everywhere. They are incredibly efficient, we know exactly how to cool them, and their power management systems are highly mature. So the proposal is to take a powerful rotary motor off the shelf, mount it in the hull, and hook it up to a transmission system.
But how does that transmission actually function? If I have a spinning shaft coming out of my electric motor, how is it making that heavy plate on the back of the boat punch back and forth?
Well, there are a few ways to do it mechanically, and all of them are pretty complex.
I can imagine.
You could use a heavy-duty crankshaft and connecting rod, operating essentially like a car engine in reverse. You could use a rack and pinion system, where a spinning gear runs along a flat-toothed metal track to push the plate out, and then you reverse the motor to pull it back.
Right.
Or you could use complex cam systems. Imagine an egg-shaped gear spinning against a flat surface. Every time the wide part of the egg comes round, it shoves the plate forward.
That sounds like it would create an unimaginable amount of strain.
Oh, yeah.
Because the electric motor just wants to spin happily at a constant speed, right?
Right.
But this transmission has to take that spin and use it to violently throw a heavy plate backward into the ocean, stop it completely, and yank it forward again, potentially dozens of times a second.
The mechanical strain is Honestly, catastrophic. The transmission has to operate entirely dynamically.
Right.
It has to handle the massive twisting torque of that slow initial startup push when the water is acting like concrete. And then it has to instantly adapt to the high-frequency, chattering vibration of cruising speed.
And doing all of that without braking.
Exactly. It is expected to do all of this without introducing excessive mechanical complexity, massive friction loss, or catastrophic heat generation.
I have to play devil's advocate for a second here, because we have had gears, cams, and linkages for over a century. We use them in heavy industrial machinery, in mining, manufacturing.
Sure we do.
If this is standard historical technology, why is it suddenly a mechanical nightmare just because we put it on a boat?
It really comes down to the medium you are interacting with. Water is an unyielding, unpredictable medium, and the load profiles in maritime environments are extreme.
Unpredictable how?
Well, a traditional mechanical linkage in a factory operates under highly controlled, predictable conditions. It isn't designed to instantly pivot from a low-frequency, massive torque state to a high-frequency, low-amplitude state.
While underwater.
Yes, while constantly submerged and fighting the chaotic shock waves of the ocean.
Let me try an analogy here. Imagine you are riding a bicycle, right?
Yeah.
You have to pedal in continuous circles, but your wheels don't spin. Instead, your pedaling mechanism is hooked up to power two giant oars on the sides of the bike that physically push you forward along the ground.
Oh, man, that sounds exhausting.
Right. Now, if one of those oars hits a massive rock, the shock doesn't just dissipate into the air. That violent stop travels instantly back up the metal chain into the gears and tries to completely shatter your pedals.
That is a highly visceral way to describe it, but mechanically it is spot on.
Really?
Yeah, when that linear propulsor plate punches into varying water resistance or, say, hits a turbulent wave, the mechanical feedback travels straight down the shaft into the transmission.
Ouch.
A normal car transmission operates within relatively narrow frequency bands and smooth load changes. Neymoten's linear stroke system demands broadband adaptability while constantly fighting hydrodynamic shock that basically wants to tear those gears apart.
So for you listening, Architecture 1 is a classic, brutal engineering trade-off.
Yeah, it really is.
You get to use proven, reliable, off-the-shelf electric motors. But in exchange, you inherit this absolute torture chamber of a mechanical transmission in the middle of your boat that is constantly trying to grind its own gears to dust.
Which naturally leads any sane engineer to ask, what if we just get rid of the transmission entirely?
Here's where it gets really interesting. Enter Architecture 2. Neymoten calls this the direct linear electromagnetic drive.
Yes.
If the transmission is guaranteed to tear itself apart fighting the water, we just eliminate the middleman entirely, right?
Conceptually, it is brilliant. In this configuration, you abandon the spinning motor completely.
Okay, so no spinning at all.
None. Instead, the electric engine itself is designed to produce reciprocating motion intrinsically. You use alternating electromagnetic fields to directly pull and push a magnetic actuator along a track.
So the engine and the propulsor plate are perfectly aligned in a straight line.
Exactly. There is no rotary conversion stage at all.
The benefits of this approach seem incredible. By removing all those clunky gears, cams, and mechanical linkages, you gain unbelievable, instantaneous control over the motion.
You really do.
The paper mentions advanced strategies here, like phase adaptive thrust and waveform shaping.
Let's break those terms down because they are basically the secret sauce of Architecture 2.
Let's hear it.
Without mechanical gears dictating the physical movement, the engine's onboard computer can perfectly tailor every single microsecond of the stroke using just magnetic force.
Just adjusting the magnets.
Right. It can push incredibly hard at the start of the stroke, ease up smoothly in the middle, and then snap back quickly. It can literally shape the wave of force to perfectly match whatever the water is doing at that exact moment, adjusting thousands of times a second.
It sounds like a perfectly conducted symphony of electromagnetic force.
It does, doesn't it?
There are no gears to break, no energy lost to the friction of moving parts rubbing together. It just sounds like the undisputed winner of the two designs.
Well, it is a beautiful theory. But this is where the physics of reality introduces a severe constraint that Neymoten is very upfront about.
There's always a catch.
Always. This direct architecture suffers from something called inertial inefficiency.
Inertial inefficiency. Okay, walk us through what that actually means for the engine in practice.
When you remove the transmission, the moving elements of the motor themselves, so the heavy internal magnets, the dense iron cores, the structural connecting rods, they must physically travel back and forth to create the stroke.
Right.
Think about a standard spinning motor. The heavy metal rotor inside just keeps carrying its momentum in a circle. It wants to keep spinning.
Yeah, physics helps it along.
Exactly. But this direct linear drive has to accelerate a heavy mass of solid metal in one direction, bring it to a complete violent dead stop, and then accelerate it back in the opposite direction.
Oh, wow. I can feel the battery drain just thinking about that. It's like working out with a heavy iron dumbbell. If you just hold it and slowly push it back and forth a few times, it's fine. It takes effort, but you can manage it.
Sure.
But imagine trying to hold that heavy dumbbell and shake it forward and backward as fast as you possibly can, dozens of times a second.
You would exhaust yourself almost immediately.
Right. And I wouldn't be exhausted because I'm pushing so much air around. I'd be exhausted because I'm spending all my physical energy just fighting the momentum of the dumbbell itself.
Exactly.
I have to spend energy to stop its forward momentum and then spend even more energy to throw it the other way.
That is inertial inefficiency in a nutshell. At the high frequencies required for a boat to maintain cruising speed, a massive portion of your electrical battery power is consumed merely overcoming the inertia of your own engine components.
That's a huge problem.
It is. The electromagnetic field has to act as a massive, power-hungry brake at the end of every single stroke, and then instantly flip polarity to act as a massive accelerator in reverse.
So we are stuck between two really frustrating extremes here. The rotary conversion architecture lets us use a highly efficient spinning motor, but gets bogged down by the mechanical nightmare of a transmission. And the direct linear drive is conceptually pure, and it eliminates the transmission, but it gets bogged down by its own sheer physical weight.
And this brings us to the most critical realization in Dr. Nemotin's paper. If we connect this to the bigger picture, both of these architectures, despite taking completely opposite engineering paths, end up crashing into the exact same wall.
The material bottleneck.
Yes. This is no longer just a mechanical engineering debate about gears versus magnets. It is fundamentally a materials science problem.
How so?
Let's look at the rotary conversion first. To survive the cyclic loads, the shock of the water, and the high-frequency vibration we discussed, those transmission gears and linkages need materials with unbelievable fatigue resistance and microscopic friction coefficients.
Because normal steel wouldn't work.
No, standard marine steel alloys will simply tear themselves apart under that kind of dynamic stress.
And for the direct linear drive, because of that dumbbell effect we just talked about, the materials problem is arguably even worse.
Oh, it's far worse. The moving components in a direct drive have to interact with magnetic fields to generate force. Traditionally, we build these internal motor components out of steel laminations.
Okay.
Steel is fantastic because it has high magnetic permeability.
Let's unpack that term for a second. Magnetic permeability just means how easily the material can channel and hold onto a magnetic field, right?
Exactly. You want a material that grabs onto magnetic forces incredibly well, the way heavy iron does. But iron and steel are dense. They're incredibly heavy.
Right, the dumbbell.
Yes. If you use them in a linear drive, the mass penalty makes the system completely unviable at high stroke speeds. You burn all your battery power just throwing steel back and forth.
So we need a material that acts like dense iron magnetically, but weighs practically nothing.
That is the holy grail Nemotin highlights. To make the direct linear drive viable, we need major breakthroughs in something called ultralight magnetic composites. We need materials that are as light as carbon fiber or advanced polymers, but possess the high magnetic permeability of heavy steel.
That sounds like we're asking for magic. Are we talking about weaving, like graphene or carbon nanotubes with magnetic dust?
It is bleeding-edge science, but that is the domain we are looking at. The paper also discusses the need for completely novel field coupling geometries.
Okay, another dense term.
Yeah.
What does field coupling geometry mean in this context?
It refers to the physical shape and spatial layout of the magnets and electrical coils.
Oh, I see.
Instead of just putting a big, heavy, solid magnet on a steel rod, can we redesign the shape of the engine itself?
Like making it hollow.
Maybe using hollow tubes or interlaced lightweight lattices so that the magnetic fields interact strongly without requiring heavy chunks of solid metal.
That's incredibly complex.
It is. The entire propulsor has to be redesigned from the molecular level up to be high strength, low mass, and capable of surviving thousands of violent acceleration cycles while submerged in corrosive salt water.
So what does this all mean for you, the listener, trying to understand the future of marine technology?
It's a big question.
It means you can't just walk into a lab, hook up a lithium-ion battery to a linear piston, and expect to revolutionize maritime travel tomorrow. Nemotin is showing us that realizing this vision requires a deeply unified system. It is a massive orchestration effort.
It truly is. You have to perfectly integrate motion transformation, mass acceleration, and complex fluid dynamics all at exactly the same time.
Right.
The electric drive architecture isn't just some secondary detail you figure out after the hull is designed. It is the central engineering determinant of whether phase-structured propulsion can actually exist in the real world.
Okay, let's pull this together for a quick recap. We started with Dr. Nemotin's foundational premise, which is challenging the century-old dominance of the spinning propeller.
Right.
Propellers waste energy throwing water sideways, and they literally destroy themselves through cavitation if they spin too fast.
Yep.
The alternative is a dynamic linear stroke. So a device that punches the water in specific phases, adapting its force depending on whether the boat is at a dead stop or cruising at high speed.
And we looked at two ways to make that punch happen. First, the rotary conversion system.
Right. The gears?
This takes our mature, reliable, spinning electric motors, but forces us to invent a transmission capable of surviving a mechanical nightmare of varying loads and brutal hydrodynamic shock.
And second, the direct linear drive. This approach beautifully aligns the engine with the propulsor, giving us absolute microsecond control over the stroke, using waveform shaping.
Which sounds great until
Until it forces us to fight the inertial inefficiency of throwing heavy magnetic mass back and forth, burning battery power, just to overcome the engine's own weight.
This raises an important question about how we evaluate emerging technologies. We often expect a new, disruptive concept to immediately outperform the old one right out of the box.
Yeah, people want instant results.
But Nemotin's paper makes it clear. We cannot fairly compare linear stroke propulsion to the rotational paradigm right now. You cannot compare a century of heavily funded, highly refined propeller technology against a nascent linear drive that is currently bottlenecked by the extreme limits of modern material science.
It's an unfair comparison.
It is simply an unfair fight until those architectures and materials are fully realized.
Which leaves us with a truly lingering thought to wrap up today's deep dive.
Okay, lay it on me.
Is the ultimate bottleneck to revolutionizing how massive cargo ships and vessels move through our oceans isn't actually about hydrodynamic design or motor placement, but rather the invention of these ultralight magnetic composites.
Right.
Could the key to unlocking the future of marine propulsion actually come from somewhere completely unexpected? What if the lightweight, highly magnetic material that finally allows the direct linear drive to work without fighting its own weight is currently sitting in a lab being developed for aerospace engineering or for next-generation quantum computing hardware?
It is a fascinating prospect to consider. The solution to moving more efficiently through the water might very well come from our attempts to move through the stars or, to process data faster.
The future isn't in spinning faster, it's in interacting smarter. And sometimes interacting smarter means waiting for the materials of tomorrow to catch up with the groundbreaking ideas of today.